Cool. So hi, everybody. My name is Andrew, and I'm a first-year master's student at UCSB. I'm going to be presenting some highlights from some in-progress research we've got going on about matrix multiplication and matrix multiplication hardware. It's being done with my group mate Zach and our advisor, Professor Jonathan Balkind, whom you just heard. So as you may be well aware, matrix multiplications are used in a variety of applications and are often a computational bottleneck. Because of that, a lot of special purpose hardware exists for matrix multiplications. So the focus of our work is figuring out how to use all of this special purpose hardware for general purpose computation. So I'm going to start off by providing some background and some history on why and how that's motivating our way forward. Then I'm going to talk about a program synthesis tool that we're building, which aids in sort of the mapping of assembly to matrix operations. That's going to form the basis for our general purpose compute language. Then finally, I'm going to finish off with some avenues we're exploring to materialize and improve this basic mapping. So to start off with some history, perhaps the most famous piece of hardware that's made the transformation from formally fixed function to near general purpose is the GPU. So traditional graphics pipelines were very fixed. Then progressively, the ability to write small shader programs emerged with a limited set of instructions, which enabled some general purpose compute, but you effectively had to make your application look like a graphics application. It was a little bit weird. In 2007, CUDA was introduced, which made it easier to write applications for the GPU without making it look like a graphics program. And of course, today, GPUs are used in a variety of non-graphics applications, with some hardware additions along the way to enable this general purpose compute without sacrificing that original graphics functionality. So what we're doing in this work is attempting to forge an analogous path for TPUs and TPU-like accelerators. So if you're unfamiliar, a TPU is effectively a specialized piece of hardware largely dedicated to matrix multiplication. I have a figure on the slide here from the original TPU paper, which implements matrix it's the matrix multiply unit, which is the main functional unit of the device. And so these TPUs and hardware similar to TPUs are in a litany of devices, with smaller edge TPUs in Google Pixel phones, larger TPUs in data centers. So the question becomes, if we have all of this new hardware, how can we use it to perform useful work if it's not being used for ML stuff at the moment? So there's been some related work in this direction by Su and Seng, which built a framework to execute non-machine learning applications with like tensor components in their critical path of the algorithm on edge TPUs. We're looking to take this a little bit further and just execute arbitrary algorithms with not necessarily a matrix component. So the performance benefits and the energy benefits of using a TPU for these sort of machine learning matrix multiplication applications, as you can see, they're pretty significant. So what we're trying to do is take the general purpose program, transform it into a series of matrix multiplications. Maybe we could see some of this benefit. So the way we're transforming our application into a series of matrix multiplications is with a program synthesis tool for the PL and the PLARCH. So I have a commutative diagram here on the slide that sort of shows the transformation from an assembly instruction to sort of the state change in the traditional ISA world. And on the bottom side is kind of the matrix inputs to matrix result. And so what we're doing is synthesizing the three functions that drop an assembly instruction down to matrix inputs going across to matrix result. And so you can have several different operations performed on matrix by the hardware, whose like specifics are defined by the hardware. We're just going to kind of stick with multiplication for now, but there could be some interesting other operations that we use. And then finally, you have this matrix result. How can you lift that back up into standard instruction state change? Okay, so the tool that we use, we basically provide a grammar for the set of allowed operations. So I'm only showing a limited set of them here to make them fit on a slide. So basically, the grammar on the left defines the first two steps of that commutative diagram. It assembles a 2x2 matrix with whose elements are essentially combined of either constants or the inputs from an assembly operation, and then multiplies those matrices. And then the grammar on the right is very simple. It's sort of the extraction step, and it just picks one of the elements out of the result matrix. So what we do is we provide grammar similar to this to Rosette, which is just a language based in Racket, which kind of embeds solver-aided constructs into the language. and Rosette synthesizes these functions for us. So with this simple grammar, we can do fun things like subtraction, which is very exciting. So to implement subtraction, you might have two register operands with two constants added to the matrix, 1 and -1. Unsurprisingly, you get the subtraction result in the upper left side. And so what we know it's in the upper left side because our synthesis tool picks sort of the 0, element extraction function for us. Also, what this leaves behind is a lot of sort of don't care sections of the matrix. That's because we're only extracting one of the elements. And I'm going to show a little bit later how we might be able to use those don't care spaces to do some other useful work and kind of pack in more information into this matrix. So to sort of sum this all up, we have a synthesis tool that sets up these matrices. Synthesis tool figures out how to kind of place these elements, what operation to do on the matrix. We only give it one operation, so that's not that surprising. And then extract one of the elements from the result matrix. So here we have some other mappings that the synthesis tool is able to do. So I'm only showing 2 bits here because I'm sticking with the 2x2 paradigm, but this can kind of extend out arbitrarily wide. So if you wanted to do shift left, the way that you would do that is basically give it all possibilities of shift left and then extract one of those elements off the diagonal. So if you had a 2-bit operand, you might multiply by shift left by 1 or shift left by 2 would be multiplying by 2 or 4. To implement AND, you would multiply sort of the component bits on the first column and first row respectively, and then extract or reconstruct sort of your result from the diagonal of the result matrix. So you might be asking yourself at this point, is it even possible to do this sort of thing on a TPU? I've kind of done some weird bit serial operations. Sort of like a register file, can I extract an arbitrary element? TPUs do kind of quantization and pack things into small 4-bit, 8-bit operands. Can I use these like 32-bit operands? And right now, maybe not so much. So part of this work is basically how can we find sort of additional constructs needed to support like efficient general purpose compute so that the TPU can become general purpose but also still be good at its main purpose in a similar style to GPU. So some paths for optimization that I am looking at the moment. On the software side, we can basically take our simple atoms of these instructions and hopefully transform them into larger matrices so that we can execute large portions of the program in a single large matrix to avoid going back and forth to the accelerator. So the first optimization is, say you had two sides of a branch, for example, and you wanted to speculatively execute both of them at the same time. Well, you could do sort of a block diagonal multiplication where A and B and C and D execute them together and then maybe extract the result once that branch is resolved. You could also sort of coalesce or unroll multiplications together. So here I'm computing A plus B plus C with 2 steps, and then A plus B plus C in a single larger matrix. And perhaps you might want to do one or the other based on some objective function. And so I put equality saturation question mark here because this might be a good target for something like that, where you have sort of algebraic rewrites with these sorts of matrix operations. And so finally, as promised, what to do with these don't care spaces. So I have 2 possibilities here. One of them is basically using them to carry control logic with the computation, which might be helpful if you wanted the matrix multiply hardware to be able to sort of compute the next location of the instruction that it is going to fetch. So here I have PC plus 4, but that's obviously just an example, but you might have something a little bit more complicated. There's also the opportunity to pack in additional operations. So in this second figure, kind of computing 2 data-independent instructions. So you can kind of think of this like extracting some ILP out of your program, whereas like the block diagonal case is a little bit more coarse-grained. So with that, I'll conclude. Happy to take any questions.